Welcome to Brain Vision.
Okay, so in this question, we are dealing with a yo-yo, and we're told that, it is accelerating towards the ground. Someone, kind of starts playing with the yo-yo and it starts accelerating towards the ground with an acceleration of 0.800 meters per second squared. And the moment in time that we are concerned with is t equals 1.20 seconds. Just gonna rewrite that. There we go. And this is, a problem in the waves chapter because as the yo-yo is rolling off the string, it rubs against the string and starts exciting transverse waves in the string as the length of the string increases. And in part A, we are supposed to show that the rate of change in lambda over time in the wavelength is 1.92 meters per second. So what we were trying to show is that d lambda dt is equal to 1.92 meters per second. We're doing this specifically for the fundamental frequency of these transverse waves on the string. So what we can do here, the first thing that we should do that will be helpful is to figure out the relationship between the length of the string and time. So what is L as a function of time? And of course, this comes back to a kinematics equation, and the one that's most pertinent here is 1/2 AT squared plus VT plus L initial. And so the thing is, and we can say V naught as well, but the thing is, the initial length of the string and the initial speed of the string are both 0. So the second and third terms drop out. So our L of t becomes just 1/2 AT squared. And we're given both the acceleration and the moment in time that we're concerned with. So from there, we can take a look at how lambda is related to L. So what is lambda as a function of L? Well, the problem tells us that we can treat both the end of the string at the person's hand as a node and the end of the string at the yo-yo as a node, which makes sense. Those are both being held in place. So that means that our lambda is going to be equal to twice the length of the string. So lambda as a function of L is 2L. So now what we want to find is lambda or d lambda dt. We have a function of lambda in terms of L, and we have a function of L in terms of t. So we can write a function of lambda, we have a function of lambda in terms of L and L in terms of t. So we can write a function of lambda in terms of t as AT squared, because 2L, lambda is 2L, 2L times 1/2 AT, or 2 times 1/2 AT is just AT squared. So our formula for lambda in terms of time is AT squared. So if we take d lambda dt, and we just take the derivative of AT squared, we'll end up with 2AT. And then we want to evaluate this at t equals 1.2 seconds. And so we can say that at the time that we care about, the rate of change over time of the wavelength of these transverse waves is equal to 2 times 0.800 times 1.20. And if you go ahead and plug that into your calculator, you will get that d lambda dt is in fact 1.92 meters per second. So that's how you do part A. Part B is a yes or no question. Now we're dealing with the rate of change of the wavelength over time, but instead of dealing with the fundamental frequency, and so the wavelength of the fundamental, we're dealing with the wavelength of the second mode of vibration. So n equals 2 now. So what we can do is we can bring back our function of L in terms of time. That is still equal to 1/2 AT squared, but our function of lambda in terms of L is different now because n has changed. So in the second mode of vibration, lambda is going to be equal to 2L divided by n, where n is now equal to 2. So since n is equal to 2, we can say that lambda is just equal to L. So this is a change from the first part. This part of the problem asks, is the rate of change for the second harmonic the same as the rate of change this part of the problem asks if the rate of change for the second harmonic is the same as for the fundamental. And we can already see that the answer is no, but we should go ahead and bring this to its full conclusion and go ahead and say what the rate of change of the second harmonic is, because it's not much more work at this point. So we have that lambda is equal to L, which means that to get a formula of lambda in terms of time, it's just the same as L in terms of time. So lambda is equal to 1/2 AT squared, which means that if we do d lambda dt, then we'll have just AT for our lambda derivative, or our time derivative of lambda. And A and T are still equal to 0.8, 0, and 1.2. And if you evaluate that, you'll get that for the second harmonic, d lambda dt is equal instead to 0.96 meters per second. And so our answer is very clearly no, they are not the same. And then, as we move on, for part C, we're basically being asked, we're given a slightly different situation where the mass of the yo-yo is increased substantially. And it's increased in such a way that its mass distribution doesn't change, so like its rotation doesn't change, and so the acceleration is still the same. And we're asked, will this change the d lambda dt for the fundamental frequency? And this question seems a little bit nebulous and weird, but it's actually, you just need to think about what is our formula for d lambda dt for the fundamental. And that is 2AT. So d lambda dt only depends on the acceleration and time, which means that it doesn't depend on mass, and so no, it will not change. The d lambda dt will be the same as it is in part A, even though we have the extra mass. So that's our answer for part C. And then part D is very similar to part C. So here it's asking, it's asking the same question as part C, but this time we're dealing with the second harmonic instead of the fundamental. So it's asking, does d lambda dt change for the second harmonic? And once again, we just look at our d lambda dt, but this time for the second harmonic, which we said was equal to AT. And once again, it only depends on acceleration and time. It does not depend on mass, so changing the mass will also not change the rate of change of the wavelength. And there you go. So we are all done, and that's how you do this problem.